It's a pleasure to come back. I like visiting this area a lot. A lot of fun people to talk to here. So what I'm going to talk to you about today is how to probe beyond standard model physics with neutrino scattering. So I'll talk about beyond that fairly diverse set of topics, but the one thing sort of putting them all together is they all have to do with neutrino scattering. So let me tell you, start with sort of the crown jewel of particle physics, right? So over the years, right, we have put together this, incredibly accurate description of nature, sort of the upgraded version of Mendeleev's periodic table, right? We have 3 generations of matter with quarks and leptons. Some of the leptons are uncharged. Those are going to be some of the stars of what I talk about today. And a very nice feature of the model that goes beyond what Mendeleev was trying to do originally is that we not only have matter here, but we also have all the fundamental forces described on an equal quantum field theoretic level as what matter is described on. And we can also explain where their masses come from. At least the masses that aren't the neutrinos, though. So there are a couple drawbacks, right? The standard model is sort of stubbornly accurate, describing most of the phenomena we encounter, but there are a few important departures from the standard model just from observation. And one of the most important of those is that neutrinos have mass. So, right, in the standard model, you can't write down a mass actually. It's forbidden by gauge symmetry. But the model gets around this by positing that there's some symmetry breaking so that we can break electroweak symmetry and give masses to the normal fermions like quarks and the electrons. But importantly, we can't do that for the neutrinos in the standard model. We don't understand actually the origin of neutrino masses requires something beyond the standard model. Hopefully also that will help us explain why they're so light compared to everyone else. And one of the other important ingredients that's missing from the standard model, of course, is that most of the mass in the universe is not in the standard model. It's something that's very, very dark, but that gravitates, something that we call dark matter. We don't know if that's one particle or a whole other sector as complex as the standard model. So we're extremely ignorant of what's going on with dark matter. We know about it from a huge number of phenomenological probes, from rotation curves in galaxies to cluster collisions, CMB precision data, and good old-fashioned gravitational lensing. And all of these point to there being about 5 times more dark matter than there is visible matter in the real world, and it's not a standard model particle. So over the years, people have sort of bracketed the approaches for how to search for new physics. So roughly speaking, there are 2 main ways beyond standard model physics could be hiding from us. It could be just beyond, if we go to this, say, coupling constant and massive particle plane. It could be, the yellow is showing standard model particles we know of, this range of masses, but with coupling constants of order 1. It could be that new physics is just beyond what we can kinematically have access to. And so going to higher and higher energies is the way to find that type of new physics. So this is called the energy frontier. So the LHC is sitting over at the energy frontier right now. And some future collider may be able to extend it a bit further to the right. But the other, qualitative possibility for where new physics could be hiding is basically right under our noses at ordinary energy scales we have access to that don't require once in a lifetime colliders, but that's very, very weakly coupled to us at coupling constants far below what we're familiar with from the standard model. So in the grand scheme of things, we really do need this multi-pronged effort if we're going to find new physics. There are arguments in both of these directions, so we really have to explore all of the experimentally accessible regions for new physics to be hiding all at once. So one framework that's started to get some attention is the idea that perhaps there is, we know there's a standard model, perhaps there's some sector, we don't have to specify too much of the details of it. Maybe it's as complicated as the standard model, maybe it's one or just a couple of particles, we don't know. But what's relevant for us experimentally is what is the portal? What's the way that these 2 sectors talk? I mean, for sure there's always gravity connecting the 2. So by portal I mean something beyond gravity. But an interesting fact is that there are some well-motivated classes of interactions to search for. So if we take sort of the ingredients that seem to be successful for the standard model, things like gauge symmetry and Lorentz invariance, there are 4 interactions that we can't turn off. We can't explain away through saying, you know, it would violate gauge invariance or it would violate Lorentz invariance, something like that. There are these 4 interactions which, if I follow the principle of the standard model, that if it's not forbidden, it's mandatory, then I have to write down these sorts of interactions. If there is some new vector particle in the dark sector, I have to write down a dimension 4 interaction allowing it to kinetically mix with our photon. I don't know the strength of the interaction, so it may be hopelessly small, but at the very least that's an interaction that's worth looking for. There are similar sorts of interactions between the standard model Higgs and scalars in the dark sector. And the final portal, which is potentially maybe the only one that's actually already been experimentally confirmed, is the neutrino portal. So if there are some singlet fermions in the dark sector, they can mass mix with our neutrinos because upon electroweak symmetry breaking, this LH term becomes a neutrino mass. So it allows the standard model neutrinos to mass mix with these singlet fermions. So there are only 4 of these renormalizable portals. So, you know, we may be ignorant of what's going on in the dark sector, but these 4 are, I think, pretty well motivated targets to go and look for. So I'm mostly going to talk about neutrino portal-oriented sorts of new physics. And since I'm assuming, too, it's a fairly broad audience, not just neutrino and dark matter people, I want to also say just a little bit about neutrinos and how we know what we know about them. So neutrinos are, you know, almost the minimal sort of particle that you could imagine, right? They're neutral. So, you know, if they were ultra minimal, all we would have to do is produce them and detect them. There's, of course, one more very important ingredient between producing and detecting them that I'll get to. But first, say we would just care about producing them. We could take some lump of quarks, a pion, for example, that can decay through an off-shell W into a neutrino and a muon, which is a heavy partner of the electron, basically. So this is one way that the standard model allows for the production of neutrinos, and it allows for their production with a definite flavor. So I know for sure I have a new mu. So now I want to detect them. I could do the same thing too for have some other way of making new e's, for example. And the way I can actually experimentally confirm that I had a new e or whatever flavor coming in is that the new e, through the exchange of a W, can convert itself into an electron. So I see some neutral thing come in that otherwise isn't doing anything, but it leaves a neutrino, an electron, basically, that appears out of nowhere. And in doing that, also converts the neutron to a proton. Neutrinos are not quite that minimal. So there's one more important step in between, which is that the flavor of the neutrinos actually changes. So I can start out, in principle, I could start out with a pure new mu beam and have nu e appear, have electrons appear. And the important ingredient in that is that the neutrino flavors oscillate. And we use this word to describe the evolution between the weak eigenstates and the energy eigenstates, the eigenstates that actually propagate. And it was the observation that neutrinos oscillate and therefore have mass that the 2015 Nobel Prize was awarded for. And again, this means that neutrinos participate in some beyond standard model physics, the origin of which we don't know. So right, this is basically a homework problem you could assign in Intro to Quantum Mechanics. Maybe it's the only example of BSM physics you could do in an undergrad quantum class. But basically, from the fact that neutrinos oscillate, we know that there's just some non-zero overlap between different flavor eigenstates. And the Hamiltonian dictates how the eigenstates evolve, right? So if I just have the most boring interaction, that have a potential of 0, then all I have is the kinetic term for the Hamiltonian. And so it's trivial to write down how the mass eigenstates evolve. And the important thing is that neutrinos are basically always ultra-relativistic. The dispersion is always basically P, but not exactly P, because the next leading contribution has this mass squared part. And it's the difference in energy values between two mass eigenstates, or energy eigenstates, that leads to this oscillation phenomenon. So that's why it's this delta m squared parameter that always appears. And right, the way I relate weak eigenstates and mass eigenstates is through some unitary matrix, which if I have a two-flavor example, is just some matrix like this. So I just control all the oscillation phenomenology from one mixing angle and one delta m squared. So just to show you, right, in principle, you could assign in your class, give them this information, now derive the probability, and, you could do that in just a few minutes or so, depending on the student, and get out all the important phenomenology you need to know about neutrino oscillation. So the mixing angle will control the magnitude of the oscillation, and the delta m squared controls the oscillation length, which basically tells you how does the energy dependence show up in the probability to oscillate. It's all controlled by this delta m squared parameter. So at the end of the day, we've assembled, now there's some large variety of neutrino oscillation observations, and which have given us, you can go look up in the PDG, all the precision information now that we've extracted out of neutrino oscillations. We know now that there are two delta m squareds, and there are three mixing angles. And in the framework of three flavor mixing, there's also one more as yet unknown CP violating phase. But these are basically the known knowns. These are things that we know, and we know them fairly accurately now. There are, for sure, known unknowns, things that we don't know in the three flavor framework. We don't know the CP violating phase. We also don't know the mass hierarchy, and we don't know, a whole lot of information about theta 2-3. We don't know, is it exactly 45 degrees, or is it a little bit below or a little bit above. Future data will be able to tell us some of these important questions about the things we know we don't know in our existing framework. But the things I'm going to talk about today are really more along the lines of things that we don't know if we don't know. We don't know, for one, even if the framework of three flavors is correct. There could be more. We also don't know, if neutrinos, in addition to participating in some new mass generation mechanism, if they also participate in new interactions. They can do new things in our experiments beyond what the standard model says they can do. So the rest of the talk is organized sort of in three parts. So the one theme is going to be trying to probe beyond standard model physics with neutrino scattering. So the first part, I'll look at neutrino scattering basically at zero momentum transfer. So this is where neutrino scattering on a background can really act as an index of refraction for neutrinos. And so this ends up modifying their oscillation probabilities. And so this is basically using the same sorts of experimental data we've used for many years in neutrino physics to understand more about exotic physics neutrinos could be coupled to. In part two, we'll go up to larger momentum transfer. And lots of things can happen as you go up in momentum transfer. This is just one example. But one thing that can happen is that above kinematic threshold, you can actually produce new states in your detector that you didn't have access to before. So I'll examine some ways that you could produce a fourth neutrino in your detector. And then in part three, we'll, the previous first two parts are basically looking at neutrino scattering today, the present day experiments, and then in the final part, I'll see what neutrino scattering could have done for us in the early universe as it relates to dark matter. Neutrino scattering may have been the way that dark matter was produced in the early universe and have some interesting interplay with phase transitions that were going on at early times. So let me now tell you a little bit about the so-called Msw effect that is probing neutrino scattering at zero momentum transfer. So this effect goes back to Lincoln Wolfenstein, who in 1977 made the observation that was the forward coherent scattering of neutrinos on a medium that has to be taken into account. So this is a standard model effect that modifies their oscillation probability. So you can see this by looking at the normal vacuum Hamiltonian. So I'm writing things in a flavor basis, which is why this mixing angle stuff appears. And in the presence of some background. So imagine I'm thinking about neutrinos as they propagate through the sun. There's some background of stuff, of quarks and electrons in the sun. And so there's some contribution from the effect of the scattering of the neutrinos on that background. So this is really, there's no momentum transfer. It's really just what's called a matter potential that comes from the neutrinos' interaction with that background. And the reason I don't have any other entries here is that, so I'm writing this, I'm imagining this being in the electron and mu flavored basis. So the sun, for example, in all ordinary matter is not symmetric with respect to lepton flavor. Right? It doesn't have a lot of muons or taus around, but there are a lot of electrons. So it's the electron part for the charge current interaction that's non-zero. There's no muons in the background. And the neutral current part I don't really care about because that's common to all flavors. So it's not going to change anyone's ability to oscillate because oscillations all come from energy differences. So I can get rid of all the neutral current stuff, and it's the charge current piece of how electron neutrinos scatter on the background of electrons that modifies the oscillation probability. So the nice thing too, right, is I can subtract another part of the diagonal so that I get the Hamiltonian in matter to basically look exactly the same as it does in vacuum, right? So I have the diagonal pieces are the same up to a minus sign, and the off diagonal is exactly the same, so that I can, if I like, just think of this along exactly the same terms as the vacuum Hamiltonian, which is just saying that now my mixing angle has a different value in the medium, right? I can define the the diagonal piece basically to tell me what is cosine 2 theta in the medium, and now it explicitly depends on the size of that interaction. It depends on things having to do with G Fermi basically of the standard model. How does neutrino interact with quarks and leptons through W and Z exchange, well, through W exchange in this case. So that's how the matter effect works. W is Wolfenstein of the Msw effect, and Dakota and Smirnov came along and fixed up a couple of the mistakes that Wolfenstein made in the first paper. So the full effect is called the Msw effect now. And this is really seen in solar neutrinos. So if I'm looking at, for example, this is the probability to convert from nu E to nu E, so the survival probability of an electron neutrino. At low energies, the matter effect is irrelevant. So it's really all just vacuum oscillations. All I need to know is some information about theta 1, 2, one of the mixing angles. And that allows me to explain exactly what that number is at low energies. But as energy increases, so for the vacuum part of the energy is basically delta m squared over E. So as I go to bigger energies, the vacuum part's less relevant. The matter part is relatively more important. And so eventually I have this suppression of the mixing angle at higher energies, which is actually seen in data. The precise sort of MSW upturn as we go from really high energies, down to moderate energies, that's actually poorly constrained. As you can see, this snow data actually prefers a downturn instead of an upturn. So current solar neutrino data will be able to probe this region. And since this is really controlling how I go from really known physics, where it's all vacuum oscillations, to stuff that's a little more unknown, that's really good at probing BSM physics. So that's one of the things I'll talk about. So, just talk about now the ordinary standard model contribution to the matter effect. So this matter potential that we were talking about before, this is all controlled by G Fermi and the number density of background fermions. So certainly people had studied, beyond standard model contributions to the matter potential. Before, this is mostly studied in what's called a non-standard neutrino interaction framework, or NSI. And most of the time this has to do with just replacing the existing matter potential by epsilon times it. So it's a simple way, and this can have some extra flavor dependence beyond what you have in the standard model, so that you have a generalized framework to search for. But one of the things we wanted to do was generalize it a bit further and consider what dark matter's contribution to the matter potential can be, and what sorts of new physics you can search for that you wouldn't be able to search for otherwise. So it's again really trying to take advantage of intensity frontier information that only neutrinos possess. So sorry, the top part of the slide's getting cut off, but so this is just to say one of the places dark matter can have a larger than normal density, since before, right, the effect is going to be controlled by not just the size of the new physics contribution. This is your model basically that tells you G Fermi prime. Also, one thing you care about is just I want to have a lot of dark matter in the background to have this effect be enhanced. One place it could be enhanced is in the sun. So there are, for example, in standard WIMP scenarios, you can accumulate dark matter that's just floating around. It can bump into the sun, and it has a mechanism for losing energy. You can start to accumulate in the sun and reach very large densities, so large that it might start annihilating, which is something you like for WIMPs. And then you can go and search for high energy neutrinos that come out of the core. So this is a known thing. People like Ice Cube, for example, go and look for that. If I imagine, though, that the number of particles and antiparticles for dark matter isn't the same, just as it is for us, there aren't an equal number of quarks and antiquarks in the real world for us, things are just a little bit asymmetric between particles and antiparticles, you can still use this solar annihilation search, if you're looking for asymmetric dark matter. But if it's really strongly asymmetric, if you have thousands or millions of times more particles and antiparticles in the dark sector, then you're never going to have any annihilation be very relevant. You're just going to be accumulating. And you can reach much more dark matter, much larger dark matter densities in the asymmetric case than you would for WIMPs, because you reach some equilibrium between capture and annihilation for WIMPs, but annihilation is never relevant if you're really strongly asymmetric. You just accumulate more and more dark matter as time goes on. But you, unfortunately, right, aren't going to be looking for high energy neutrinos from annihilation in that case, but you can look for a modified matter potential. So, yeah, this is again basically saying the same thing, right? We need to go look for regions of high dark matter density. We have to have some model for how neutrinos and dark matter interact. And one important effect is that this really needs to be asymmetric, not just to get a big number density, but also because the matter potential is equal and opposite between particle and antiparticle. So if I have equal numbers of particles and antiparticles in the sun, I'll have zero effect. The two matter potentials just cancel out. Right, I want to think about how do I get dark matter in the sun. So the basic idea is to borrow what happens for WIMPs. So I have some cross-section for dark matter and nuclei that allows dark matter to accumulate in the sun. So this is something that can be probed with existing data. And you can turn that, basically just by looking at how dark matter slows down as it exchanges energy with the medium of the sun. You can go and turn a cross-section into an amount of dark matter that can accumulate in the solar core. And lighter is always better. It will always give you a bigger number density. For one, the limits also get weaker. The number density goes up. The limits get weaker, but eventually you're constrained by this evaporation limit. So there's a countervailing consideration, because in the core of the sun, right, it's not just a cold place, it's a fairly hot place. And so a nucleus can come over after you've already been captured and inject additional momentum to you such that you go above the escape speed of the sun. So this is called the evaporation process, which really wins out over everything else for dark matter masses below 4 or 5 GeV. But nonetheless, you can accumulate a fair amount of dark matter in the sun. And one interesting effect that's very different from what happens, say, for NSI, for other modifications of the matter potential. One thing that's very different is that dark matter, is not confined, is not floating around the whole sun. It's really confined to the very inner core of the sun because it's a fairly heavy mass. So we have here for 10 GeV is this sort of orange shaded region, which is where most of the density for 10 GeV or dark matter particle rather would be, and 5 GeV is a little more spread out. But the important thing is that I'm not going to affect all the different production regions of solar neutrinos equally. So, right, in addition to producing neutrinos with different energies, all these different processes in the sun that give us neutrinos take place at different radii. The fraction of the flux that they contribute to, is spread out in the sun. So, for example, dark matter is not going to do anything to the N13 contribution from neutrinos at all, because although there is a lot of ordinary matter out there, there's no dark matter. So this is another potential signature to look for, in addition to modifications of the electron neutrino survival probability. So this is the main data that we fold in this plot. So I'm imagining, as one example of a beyond standard model physics Lagrangian for how dark matter, which is X, could be interacting with neutrinos. So this is this A is not the photon, but basically a Z prime or a dark photon, some dark sector vector that connects dark matter and neutrinos. So it's along very similar lines to what the matter potential for the standard model looks like. So if I allow this interaction to turn on, there are other considerations too to think about. I have to worry about how neutrino propagation from large distances is modified. So things like supernova 1987A and also Ice Cube place some constraints on this sort of interaction. Also, right, I also allow dark matter to talk to itself, so it can self-scatter. This is actually limited by things like cluster collisions, like the bullet cluster. And also, importantly, I would allow, at fairly late times in the universe's history, allow for relativistic neutrinos to exchange momentum with dark matter, which could heat up dark matter too much. So anyway, I take together these different constraints on this type of model, and those are all represented by these black curves in the plane of coupling constant and mediator mass, the mass of this A vector mediator. And what we see in the pink to red regions are different regimes where the matter potential, when it's a border, the standard model matter potential, where this could be the most sensitive probe. So basically starting around, mediator masses, I guess this is around 0.1 or maybe 10 to the minus 2 eV, does these probes from the sun or even just the halo. So the halo would be from no accumulation, right? If I turn off any of the dark matter getting trapped in the sun, but just consider the halo density of dark matter, so basically the automatic density, then I would get this this red region. So yeah, this is an interesting probe, and right, certainly gives you access to dark sector physics that you otherwise would have no hope of probing, right? Far beyond what Ice Cube or Lyman alpha or certainly dark matter self-interactions can probe. Okay, so let's go up in momentum transfer and consider a different class of DSM physics we can go and look for, but still using neutrino scattering as the main probe. So right, so as I was saying before, right, the existence of neutrino masses really implies something new, right? We don't have a way to write down masses in the standard model, right? It just breaks gauge symmetry, and we get around that through the Higgs mechanism. We say, the electroweak symmetry is spontaneously broken through the dynamics of the Higgs field, and that's what gives us ordinary mass. But it doesn't work for neutrinos. I don't have right-handed partners around. But the simplest explanation, right, as you might think, is just make neutrinos like all the other fermions and have some right-handed partners, so that I can start writing down some mass terms and explaining the origin of neutrino masses in this way. So these are usually called sterile because they don't participate, they're singlets under the electroweak symmetry, they don't participate, don't scatter with W's and Z's. And right, we also don't know, of course, if neutrino masses are Majorana or Dirac. But, you know, didn't say all neutrino mass models, but almost all have someone like this around to explain neutrino masses. So how do we go and detect them? I think the best case scenario is to really make them in your detector yourself, have it in your detector volume, and to use cheap neutrinos. So I'll just use natural neutrinos for this. So the first probe I'll talk about uses the Ice Cube Detector. So this is a detector that's buried in naturally occurring ice in Antarctica. It's a cubic kilometer of instrumented ice. It's very, very, very pure ice that's itself a kilometer deep. So they had to drill down and then instrument this volume of ice with these digital optical modules, which are, you know, sensitive photon detectors for detecting the Cherenkov radiation that's produced when a high energy neutrino comes in, scatters in the ice, and makes a bunch of charged particles that produce characteristic Cherenkov radiation. And so Ice Cube, in addition to looking for atmospheric neutrinos, also has found an unknown source of astrophysical neutrinos all the way up to PeV energies. And they're doing a lot of exciting things. The thing I'm going to talk about has to do with using the atmospheric neutrinos as a PSM probe. So this is just a schematic of the Earth with the atmosphere. So the Earth being bombarded by cosmic rays. We have Ice Cube, which is big but not drawn to scale here. It's not that big. So right, cosmic rays come in. They'll hit some air molecule in the atmosphere and produce some shower of pions. And right, like we know from before, if you have pions, you have neutrinos. They're going to decay, give you characteristic flavor ratio coming from the pion and muon decays. So your detector, Ice Cube, is going to be bombarded by these naturally occurring neutrinos at a range of energies. And I could, in principle, go and look for the production of a sterile neutrino in the Ice Cube volume from the fact that, by the fact that the sterile neutrino mass mixes with the ordinary neutrinos, there's some probability for it to be produced directly, depending on that mixing angle. And so the way I would produce this is basically by using topological information. So the way that Ice Cube can tell the difference between different flavors of neutrinos is really simple to understand just visually. So it comes from, so this is simulated data. Sorry, these two are actually real data, and this is a simulation. So you can see the strings here, and the size of the blob represents how much energy deposition a given digital optical module gets, and color is telling you redder means it happened earlier. So I know that if a new mu came in and through a charge current interaction produced the actual muon, came from this direction, red came first, and just went through the whole detector. Muons are long-lived and don't lose a lot of energy, so it just streams through the detector, making this nice track. And basically all the other types of interactions, any charge current that's not a muon and any neutral current interactions gives you a much more spherical energy deposition, where you have, essentially one very big, collision on the hadronic side. It deposits most of the energy. So these are probably just called cascades. These are called tracks. And the other possibility, which is just seen in simulation, not seen in data yet, is what's called a double bang. So a new tau comes in, the hadronic side of the interaction produces the first blob, and the tau that you've produced in the charge current interaction travels a physical distance, some tens of meters, before it decays and leaves another blob. So right, this is only in the standard model, this can only happen for energies above a few PeV. So there's, they should see them soon, but they haven't seen these sorts of events yet. But through mass mixing, sterile neutrinos can do a very similar thing. So I've come in with some active neutrino naturally produced from atmospheric collisions with cosmic rays. He comes into my detector and can produce, right, with a probability controlled by the mixing angle, can produce the sterile, which then travels some visible distance before it decays. I can go and look for a double bang like that. I have to worry about constraints from other experiments on the mixing angle for the sterile neutrino. And this is indeed fairly strong for mixing with the electron flavor or the mu flavor, but it's surprisingly weak for the tau flavor. And this just comes down to the fact that tau neutrinos are pretty hard to produce in the lab, so the constraints on mu tau mixing with a fourth neutrino are surprisingly weak. So shown here are some existing searches from CHARM and Delphi. So right, the other thing is that, right, so we're agnostic in general about what the mass of the sterile neutrino is, but as you scan over different masses, different decay channels will open up, just kinematically. You're controlled by what the standard model tells you can decay to. So we include all the possible decay channels. If it goes back to neutrinos, which it has with some probability, that unfortunately won't produce a double bang, right? That'll just be a single bang you see on the hadronic side and then nothing from the second bang. But just to set the scale, for a GeV sterile neutrino with mixing squared of 10 to the minus 3, and say it has a 10 GeV boost, right? This is also something you have to worry about. How do I fold in, convert the atmospheric flux into some spectrum of energies that the particle will be produced with. But if I have 10 GeV as a boost, this will give me a decay length of around tens of meters. So around the scale that I need for Ice Cube. So this will be the scale roughly that Ice Cube's able to probe. And indeed, when you go into the detailed Monte Carlo, it goes down even down below 10 to the minus 4 in the full Ice Cube volume. And nicely sort of filling in the gap between CHARM and Delphi. So this is, and also, right, to emphasize too, these are much lower energy double bang events. These are not occurring at PeV energies like the standard model would predict. So this is just a sensitivity estimate for producing one event in 5 years of atmospheric neutrinos at Ice Cube. So there's no, Ice Cube hasn't done the search themselves. There's no reason for them, prior to this paper, there's no reason for them to go and look for double bangs in atmospheric data. But hopefully they'll do that in the near future. Right, so this is really just existing data, so there's no good reason for them not to do it. Yeah?
So this involves seeing a lower energy bang at the initial flavor changing vertex from the hadronic shower there.
Right.
Can we see that at the start of muon tracks already?
So what do you mean exactly? So if I go back to...
So that's a track that comes in already in muon.
Right.
But if I produce a muon inside the volume, which surely...
Oh, yeah, sorry.
We can see that bang, right?
Yes, so you're saying at lower energies,
Yeah.
muons can also fake this somewhat.
No, I'm just saying how visible is the bang versus the muon track in that production? Because that is the hadronic scattering. You're going to get the same generic behavior there.
Right. Oh. So you mean...
How much does
with
a
a
single
muon
bang at low energies depend on the electron being there also versus just the hadronic crap?
The electron being there. So
your central data one is also, the single bang would also be exactly what you would expect maybe from this thing if you were a sterile neutrino decay back to 3 neutrinos.
Right.
How much of the energy deposited there is coming from the electron versus the hadronic crap?
Right. No, I don't really remember that number. Yeah, that's a good question. Right, I mean, so the other thing, right, to say about the background that we have to worry about, right, the other important thing we had to fold in is the amount of fake double bangs. I mean, is this getting to your question?
Yeah, it's just how clear
yeah.
is the doubleness of this bang is kind of the question.
Oh, yeah. So if you wanted to estimate from, say I take the atmospheric flux, and just calculate the probability to misidentify, to say, just because the flux is so large or something, I see two bangs next to each other that are not from the same event.
So there's that.
There's
And
that.
also
That's
the,
a low probability.
what are the odds that I just say, that's some random noise over there, and I see one event?
Well, what random noise? What do you mean?
If my hadronic scattering was soft,
Well,
say or if my muons characteristically look like just a muon, and I don't see much hadronic activity from them,
Right.
then I should expect not much hadronic activity from my neutral current flavor change. And I might not characterize that as two bangs, really. I might say, well, here's a bright thing, and here's some noise in a few of my detectors.
I mean, the process we're thinking of is all neutral current stuff, right? Yeah, I think I still don't see what your question is exactly. So for the main background we had to worry about, right, was this double coincidence of fake double bangs.
Right.
But you're saying,
I'm just saying, how loose is your definition of a bang to be sure that you see two of them in all of these events?
So in terms of, another way to say one of the searches that they do is what's called a double pulse event. So this can actually get to finer, smaller decay lengths than what, this tens of meters that I was talking about. So in that case, I mean, if I remember right, this is like at the tens of nanosecond level or something. I mean, to give you an idea of how we're defining what a double bang is, right?
Yeah, I just don't know, because hadronic physics is hard, how bright that first bang is in a neutral current.
Right.
Event.
Oh. So like what fraction of the energy?
Yeah.
So, I mean, this is controlled by the inelasticity parameter, which I think is like 0.3 or something at those energies. So I think it's like 30% of the initial energy.
That should be fine.
Yeah. Okay, sorry, now I finally get your question. Yeah. So right, this is something that, yeah, that's right. So that's a non-trivial thing that you have to calculate. And yeah, thankfully someone else calculated a long time ago, so it was just a paper I referenced. Yeah. So there's a nice paper from, I think it's Gandhi, Quigg, and Sarsevich that did these calculations in the 80s or 90s or something. So yeah.
And they should be.
And it depends on the energy for sure.
It should be testable by looking at
Yes,
tracks and
yes,
seeing
that's a good
bang
point.
part
That's a good
of
point.
on track.
Right.
So we
Yes.
can extract it from current data to confirm that.
Yes, which I assume has been done, but that's a good question. I don't know if that has been done. But that's an interesting question. Okay, thanks. So this is sort of a super minimal framework for searching for sterile neutrinos. Another question which maybe we should ask ourselves more and more is, what other sorts of interaction mechanisms can we think about and search for sterile neutrinos, right? This is one that's automatic. It's one that I say I have a sterile neutrino and I have a given mixing angle. That just is what happens. It's the same thing that controls neutrino masses. But another possibility is that sterile neutrinos could also interact through some non-renormalizable interaction. So they could have some transition moment, basically a magnetic moment, but one that's off diagonal on neutrino planar that connects ordinary active neutrino to a heavy one. So this is another way of producing a sterile neutrino in my detector. And in a certain sense, right, if this is the only term in my Lagrangian, he's not really a sterile neutrino, it's just a neutral lepton. Right? If I don't posit any mixing with the active neutrinos, he's not a sterile neutrino. It's just some neutral lepton that I can probe in my scattering event. And it's the same, so this is what controls the scattering, to produce him in the first place, and also controls his decay. So this is another set of physics we can go and search for with existing Ice Cube data. So now all my unknown is the scale of that magnetic moment and the mass of the new state. So this is sort of playing the role of the mixing angle from before. And again, for new tau interactions, the constraints can be many orders of magnitude better than existing data. So Donut, which is the discovery of the new tau experiment at SLAC, that was one of the only existing limits on this interaction at our masses that we were interested in. But even in the case of new mu flavor, we can actually go beyond what existing constraints could say. So for example, with charm and nomad. So this is another, I think, pretty interesting interaction to take a look at. And an sort of general point for really making the best of all the experiments we have at our fingertips right now is, we don't necessarily always need some, multi-billion-dollar experiment to do new physics. We can oftentimes just reinvent, we don't have to reinvent the wheel. We can repurpose existing experiments to go and look for new physics. So another way we could look for the same interaction, this dipole portal interaction for sterile neutrinos, is with direct detection data. So this is something people here know a lot about, but just in case you haven't heard about this, the basic idea is to use a dark matter detector, an experiment designed to look for the small energy deposition from dark matter colliding with the nucleus. Eventually, right, these experiments are going to run into backgrounds from natural neutrinos, from solar neutrinos at the lowest energies, and also the diffuse supernova background and atmospheric neutrinos will contribute at higher energies. So this will become some floor to these experiments as sensitivity for these experiments increases. And potentially be even detectable right now if neutrinos participate in some new interactions. So, right, also, there's a nice review that's a day or two old. You could go take a look at from some of your colleagues here, Bhaskar and Louis. So this is just to point out, right, there's also many of papers not cited here. There's a huge, this is a big direction a lot of people have worked on, so it's not an exhaustive list, but includes papers by many people in the room, I think. So we took a look at a type of interaction that's mostly not been studied in this regime. So we wanted to look again at this neutrino portal interaction, go and use just solar neutrinos. And right now, with existing data, existing xenon 1 ton data, we can exclude a small region of parameter space beyond what Ice Cube and beyond what Donut has already been able to do. And with future data, super CDMS will be able to go even farther and in particular close off this gap that between basically Donut and Ice Cube and down here where a paper that appeared just a few months before ours that used supernova data to rule out this small window of parameter space. So there are a lot of interesting things you can do, I think, with direct detection data, going to look for, worst case scenario, we don't see dark matter, but maybe we can still probe other types of beyond standard model physics. So, right, all that I've talked about so far is neutrino scattering at present day times. So in the final part of the talk, which is very short, so I'm almost done, I'll talk about neutrino scattering in the early universe that could have been the origin of dark matter. So, right, first, the important thing just about the framework for sterile neutrinos is that unlike the other fermions, most of the time we think about in PSM physics, the number of them is not controlled by any anomaly cancellation arguments. I don't have any good reason for stopping, when I write down these singlets. So we don't know how many nature has. I'll have Dirac masses I can write down with these sterile neutrinos and my Higgs and ordinary lepton fields, and also potentially Majorana masses. We don't know how many of them there are, but we know we have to have at least two of them if we want to explain the two delta M squares for atmospheric and solar neutrino oscillations. And if you have a third one, and you want to explain neutrino masses, then you can also explain dark matter. So this is sort of the framework people have in the back of their minds when they talk about sterile neutrino dark matter. They actually, most of the time, don't have in mind just one sterile neutrino. They have in mind three. But it's just one that's relevant for dark matter. So again, right, now everything's controlled by the mixing, so it is a sterile state, but it inherits some fraction of the standard model interaction just through mixing. So the sterile neutrino production cross-section is basically going to be controlled by standard model scattering, stuff I know very well, and some mixing angle. So this is an idea that goes to Donaldson-Woodrow in 1993, and it's a very elegant way of producing dark matter that's unfortunately excluded by data, and I'll talk about a way around that. But the framework is very simple. You basically just put oscillations, which are all lumped in with this matter-dependent mixing angle, and collisions, which are controlled by this gamma, and that's all controlled by standard model physics, and then oscillating in some, colliding and oscillating in some expanding universe, which is controlled by the left-hand side. And so, right, also notice that I'm looking at the number density, basically, or occupation density of active neutrinos here that's producing an occupancy of sterile neutrinos on the left-hand side. So it's really from those sorts of collisions here. I'm producing, from my background of active neutrinos, producing some sterile neutrinos in the scatter. And it's very nice. You can do it even analytically, estimate what is the mixing angle that I need to produce the right abundance of dark matter. And it's some tiny mixing angle. Unfortunately, not so tiny it hasn't been excluded though. Right, the other important thing to say is when is all this happening in the early universe? Right, you have to, of course, to do detailed predictions, you have to solve this Boltzmann equation. But the peak of the production, you can get order of magnitude this estimate just by looking at the peak of production, which occurs basically when the collision rate and oscillation rate are comparable. And this happens at around 100 MeV timescales in the early universe, or temperature scales, I guess I should say. So the way you detect this type of dark matter is that it's unstable. So through loop diagrams, by inheriting a bit of the weak interaction, I also can decay. And the one that's always open is always kinematically open is going to some final state that's an active neutrino plus a photon. And since this is a two-body decay, that gives me a line, a delta function in photon flux, which is very easy to search for above background. So if you go to higher masses, there are other things you can worry about, like decay to electrons, and then you get some spectrum of photons out. But if I care about having some baseline sanity check, like I want him to be stable on universe timescales, that can give me some, fairly weak bound on the mixing angle. But if I combine this with the estimate from before for what I need for the early universe physics, this limits the ability of Donaldson-Woodrow up to around 700 keV masses. I want them to be stable. But X-ray limits are strong enough to rule out the whole parameter space for Donaldson-Woodrow production. So I showed some of the most recent X-ray limits using new star data that were from this year, and shown for reference are a potential signal of decaying dark matter. So there was a lot of excitement a few years ago about a signal, an X-ray line, that could have been due to sterile neutrino dark matter. It seems to be excluded based on other constraints. And moreover, here in this plot, Donaldson-Woodrow line is not even drawn because it's many orders of magnitude away. Here you can actually see it in this broader parameter space. So where it would need to be to get the right amount of dark matter is just on this black line. Eventually, right, I'm limited around, 700 keV or so, just by the stability argument. But whatever it is, I'm strongly ruled out by this mass region integral limits, and then over here new star and other limits. So unfortunately,
so,
it's nice.
So when you calculate that dark matter abundance from this, is just it's already abundance is already frozen in from the new sterile neutrino. So that's the.
So you mean in the Donaldson-Woodrow?
Yeah.
So right, the idea is that I solved the Boltzmann equation for this, right?
Yeah.
So it tells me what is the mixing angle I need to produce the right abundance to get omega 0.2.
I see.
Yeah. And so this is the mixing angle you need. So that's that curve that I was drawing before is this equation.
I see.
Yeah. Yeah, that's right. So basically, the way to think about it, this is the target, right? To go and look for the X-ray astronomers to go and exclude. And it's been excluded by quite a lot. And it's a very nice, minimal production mechanism for dark matter. It's also a model of dark matter potentially connected to neutrino masses. So I think it's worth thinking a little bit more too about ways that it could still be allowed by X-ray data. And one simple way is if these singlet fermions that are dark matter, if they couple to a new scalar, a singlet scalar, that could explain where part of the Majorana mass comes from. And I just imagine something like a Mexican half potential, like the ordinary potential we have for the Higgs. In the early universe, there are finite temperature corrections so that it's really driven to phi equals 0. It's basically all quadratic at high temperatures. And then you drop the temperature and there's some critical temperature where a second vacuum appears and you're driven to, which is the true vacuum at 0 temperature, and you're finally driven to roll down the hill and have finite vacuum expectation value and generate a new Majorana mass. And that's great because in the seesaw framework at least, where I have big Majorana masses compared to Dirac masses, the mixing angle is controlled by the Dirac mass divided by the Majorana mass. So if the Majorana mass is small at early times but big at late times, it allows me to offset what Donaldson-Woodrow needs to get the right abundance and the X-ray constraints. So this is just an example with that Mexican half potential, how the VEV develops with temperature. So as I drop, right, say follow the green curve, which is I'm fixing lambda, the quartic coupling, eventually, I get to low enough temperatures that the VEV starts rising up and then asymptotes to 0 temperature value. And I can turn that into a mixing angle, into a seesaw framework that interpolates between some high temperature mixing angle that I need to get the right dark matter abundance and, driven to low values to get away from the X-ray constraints. And the other nice thing that the framework just predicts, that is not put in or anything, but it just comes out, is that since the Majorana mass is the main contribution to the total mass of dark matter, and that mass grows, it grows after I produce the abundance of dark matter, this produces colder dark matter, right? Because I produce a 1/2 MV squared of energy with a given mass, and that energy remains conserved, but the mass doesn't. The mass gets larger as time goes on, so the average velocity of dark matter has to go down, and it produces colder dark matter than what you'd get from the ordinary Donaldson-Woodrow production. So this is, I didn't say, but this final part of the talk is not done. It's the work in progress. So tell me now if you see major problems. But that's something I'm working on now that I think is pretty fun.
Yeah, just go.
Yeah.
So suppose somehow if I make the dark matter mass to be little bit heavier in your total circuit drawing energy, then would I be out of this mess?
So do you mean through something like?
Suppose I change the expansion. And that would change your.
Oh, changing the expansion rate.
Yeah.
You mean as another way to get around?
Yeah. So that may require larger dark matter mass from you.
Maybe. Well, yeah, maybe that would work.
Balance doesn't exactly get weaker at higher dark matter mass.
Easy. So that's I forgot.
Do you mean? Oh yeah. So I mean, if you look at the constraints, it's at higher mass they get stronger.
Okay.
But so this is the reason it gets stronger too is easy to understand. So it's because the fact that the decay rate is going as the 5th power is because the decay is basically G Fermi squared times mass to the 5th. And so as you go up in mass, the rate explodes very quickly. I think your general feeling is correct that there probably are other ways of getting around this sort of tension, because it's surprising to me it hasn't been more explored. The main thing people have in the back of their minds that has been explored is a Lepton asymmetry. So as you turn that on, then the early universe story is wildly different, and you cannot do it analytically, but it does allow you a way to offset early universe predictions from X-ray constraints. But it requires like a density matrix formalism and supercomputers to do the right abundance calculation. It's way more involved. But my guess is there are a lot of other BSM frameworks that would do similar things that have not been explored. And I think we should think more about it. I mean, it's a very nice, minimal type of dark matter, you know, also connected maybe with neutrino masses. I think it's very motivated.
Yeah, so the only thing is I can clearly see how Hubble would be the correlate.
Well, I guess it would be in G star, right?
In
So,
G star. So
this is,
so if
you make this bigger,
suppose if I raise Hubble,
that's worse actually, right?
that's worse.
Because then yeah,
So then
Because
I
you
need
get less
to lower
time
Hubble.
to generate this stuff, and
Yeah.
that'd be efficiency,
right,
is the physics there.
yes.
So
that's right,
that means
that's
I
right.
need to lower Hubble.
Yes.
So
But
suppose
you
I have
can't-
a matter dominated phase.
Ah,
Right? So
yeah, if it was matter dominated at hundreds of MeV?
Yeah, because
Does this mess up BBN?
No,
Well,
then you have
one
to-
MeV.
Oh,
Because,
one.
Up to BBN is
Right, that's
radiation
true.
1 MeV.
Okay.
Suppose at 100 MeV, because
Yeah.
all these moduli, that would be corresponds to
No, but-
moduli mass scale.
But Bhaskar, then you're going to have a situation where your matter all decays and it dilutes back away any abundance you make.
Hmm. Well, unless
Right,
it's
this is the
something
usual
else.
way of
No,
dealing with an
No,
overabundance.
use so much dark matter, even if you dilute, you won't dilute away everything. So it's like between 100 MeV to order 1.
Yeah, if you could set Hubble rate to 0 temporarily and just sit there resonantly producing this stuff for a while, maybe you could pull it off, but.
Yeah, matter domination.
Yeah, maybe.
But anyway, I see the point.
So let me just put up my conclusion. So, yeah, the main theme in the talk was that the two sorts of elements I'm really interested in for beyond thinner model physics are the existence of dark matter and also neutrino masses. And I've worked on a couple different directions, but one unifying theme through the papers I talked about today is that they all involve neutrino scattering as a way of probing new physics. So right, we can maybe extract some information about dark matter and neutrinos from future oscillation data. Could potentially produce sterile neutrinos in our detectors directly, either at direct detection experiments or at Ice Cube. And neutrino collisions may have produced dark matter directly in the early universe. So thanks a lot. Thanks for your questions. Any other questions or comments or anything?
Is there a reason that kinetic energy is the thing I should think about as I go through this phase transition and not say the linear
For
momentum
coldness?
of any given particle?
To describe the coldness of it?
Yeah, to describe the amount by which it gets cooled.
Right. So the argument applies for momentum too, right?
Well, but this gives me a different scaling of the velocity.
Oh, because, okay, so that's interesting. If, okay,
Doesn't it?
yes, I guess that's right. If
I've
the
never really known how to
average,
think about the changing mass of a
Right.
particle on either
So-
side of a slow phase transition. I know with the bubble walls, you get the whole chiral reflection
Yeah.
fun stuff.
So I know for, I know for other production mechanisms, so another thing people have considered is getting sterile neutrinos from the decay of a scalar, some heavy scalar, so something not Dodelson-Woodrow, right, but some extra degree of freedom freezes
Yeah, this
out
is
and
like
then
superwind,
decays.
yeah.
Yeah, exactly, it's similar to superwind, yeah. And yeah, again, there, the main thing they worried about were things like Lyman alpha structure formation charts with constraints are p-squared, and they got it from an energy conservation sort of argument. So I don't know actually the answer to the question now. Why not momentum? Since that does have a different scaling.
Yeah, I just have no idea how to think about
Yeah.
that particular physics.
Right. Yeah, that's a good question. So I need to think about that. Anticipating referee criticism.
Yeah,
absence of our usual organizers and in absence of any further questions, let's thank you again.
What happened to
Thanks.
the rest of the crowd?
Sorry?
What happened to everybody else? Like,